All right, let's get into it. We are going way behind the scenes here, past all the warning signs, to really uncover the story of how X-rays are born. And believe me, it is an incredible story of speed, insane energy, and these tiny, tiny microscopic collisions. You know, whether it's for a broken bone or just going through airport security, we totally take for granted this almost magical power to see inside solid stuff. But here's the thing. It's not magic at all. It's physics. And it turns out it's a surprisingly violent and, honestly, a beautiful process. The hero of our entire story is a particle you already know really well, the electron. But this is not just any old electron. Oh no. This one is about to get shot on one of the most energetic journeys you can possibly imagine. So where does all this high drama take place? Well, our arena is a super specialized piece of tech, the X-ray machine. And you might be kind of shocked to find out that for all of its power, this is also a story about incredible inefficiency. Okay, get this. This number is just staggering. For all the raw power we pour into an X-ray machine, a full 99% of that energy is instantly wasted as heat, just gone. That's why these tubes need these massive cooling systems. Only a tiny 1% actually becomes the X-rays we need. It's an incredibly powerful process, but man, is it inefficient. So at the very heart of the machine is this thing right here, the X-ray tube. See, on one end, you've got the cathode. That's our starting line. And way over on the other end, there's the anode. That's our target. And everything inside is a vacuum, which makes sure our little electron has a perfectly clear path for its super high-speed journey. Now, this is where the action really starts. We're about to take our electron and give it this unbelievable push, launching it from a dead stop to a huge fraction of the speed of light, and all in the space of just a few centimeters. The whole process is this really simple but incredibly powerful three-step launch. First, we heat up a filament, kind of like in an old-fashioned light bulb, to boil off a whole cloud of electrons. Step 2, we use a massive voltage difference to just grab those electrons and hurl them across the vacuum tube. This gives them a ton of kinetic energy. That's the energy of motion. And finally, the moment we've been waiting for, generation. The electrons just wham! They slam right into a metal target, the anode. And this is where the magic really happens. All that speed, all that kinetic energy, it has to go somewhere, right? The electron smashes into that target, and in that impossibly small moment, one of two things is going to happen. It's basically a game of atomic chance. So, our little speeding electron can either have a near miss with the nucleus of a target atom, or it can score a direct hit on one of that atom's own electrons. And each of these two fates creates a totally different kind of X-ray. Okay, let's check out that first fate, the near miss. This is actually the most common way X-rays get made, and it's got a pretty cool name that perfectly describes what's going on. It's called Bremsstrahlung, it's a German word, and it literally translates to breaking radiation. And that is exactly what's happening. The electron is slamming on the brakes, hard. Okay, here's the breakdown. Our negatively charged electron is zipping past the atom's huge positively charged nucleus. That positive charge yanks on the electron, right? It causes it to swerve and slow down, just like hitting the brakes on a car. But all that lost energy, all that motion, it has to go somewhere. So it's instantly released as a tiny packet of light, an X-ray photon. But what about that other possibility? What happens when our electron doesn't just put on the brakes, but actually causes a head-on collision? Well, that creates a completely different and very specific kind of X-ray. Honestly, the best way to picture this is like a game of atomic pool. Our projectile electron is the cue ball, and it's about to slam into this perfectly arranged rack of electrons that are all orbiting the target atom. It's a whole chain reaction. First, the collision. Our projectile electron comes in hot and just knocks an electron clean out of one of the inner shells. Now there's an unstable empty spot, a vacancy. Nature can't stand that, so an electron from a higher, more energetic orbit immediately drops down to fill that spot. And as it falls, it has to release all its extra energy. And it does that by spitting out a single X-ray photon with a very specific or characteristic energy level. So you've got these two totally different things happening, the near miss and the direct hit, millions and millions of times every second. Now let's see how they actually come together to form the X-ray beam we can use. This graph you're looking at, it's basically the fingerprint of our X-ray beam.
See that big smooth curve? That's all the braking radiation. It's a continuous spectrum, which just means it has a whole range of different energies. Because, those near misses can happen at any distance. But do you see those sharp spikes?
Yeah, those spikes are the characteristic X-rays from the direct hits, each one with its own precise energy level. And check out the contribution here. The huge majority of the useful X-ray beam, sometimes nearly all of it, comes from that braking radiation. The direct hit radiation makes up a much smaller but super distinct part of the whole picture. So, after all that incredible acceleration and collision, all that braking and atomic billiards, we're left with that tiny but unbelievably powerful 1%. It's a beam of pure energy forged from microscopic violence. I mean, it is just an amazing process, isn't it? Two different kinds of collisions, a near miss and a direct hit, happening on a scale we can't even see, that we've managed to harness to give ourselves a superpower, the ability to see the invisible. It really makes you wonder, what other secrets are just waiting out there, waiting for us to send the next particle on its journey?